Hi, I am Peter Bøggild. I'm sitting in my garden, so it might be a little bit noisy depending on the neighbors and the birds and whatever power tools they may choose to use. Not the birds, obviously. I'm going to talk to you about interactive learning tools. These are HTML programs that we use to blur the line between visualization and physical models and blur the line between static learning materials like textbooks and lecture notes and programs that the students can use to encode their own learning experience. And we use AI programming to do this, something we worked on for maybe 1.5 years, and we already deployed in teaching. For me, interactive simulations and visualization is nothing new. I've worked with this for around 20 years in the courses I've been teaching. But I think that AI programming is a game changer, and I'd like to show you some of the things that can be achieved in very short time using the tools that are available today. So let me show you what this is all about. This is a guy jumping on a diving board. So you can see the diving board is having a specific curve. This object is called a cantilever in mechanics, and we can calculate how the stresses are developing, like where the stress in the material is largest, and also the relationship between the force that presses down the diving board and how kind of in this curve, like how deep it depresses. And this is a way to do it is by finite element simulations. This is visualizing how finite element works. So like splitting up the object into small objects that are like linked through mathematical equations. And here in this method allows you to calculate exactly where the stresses are largest. So here you can also see where the diving board would break, should it break. But I can give this code, this small HTML program, I can give this to the students and ask them to make more sophisticated versions. So let me show you what I mean. So this is same as before, but now the students can have like a way to change the mesh size by moving the cursor along the cantilever. And here you can also see that as I press down here, when the mesh size is too coarse, then there's more discrepancy between analytical and the finite element, like numerical results. Whereas when you having a fine mesh size, you have a much better agreement. You can also turn this into something that explains the physics to any depth. So you can have this as like a portal that opens up and expands and unfolds as you dig deeper. At this, there's just one level here, but there's absolutely no problem in kind of making this a tunnel of knowledge that expands and develops into a full mechanics course. You can have reflective questions and exercises and quizzes, and you can have go more on the implementation in the finite element simulation and learn about that. This is all something the students can do, or I can do, and we can do together. So another example is this figure here from a textbook I use on first year physics. This is showing a graphene lattice, and these small spheres represent atoms with bonds in between. But why make it? But when the students look at this, it's a little bit abstract, and maybe it makes more sense to show them something like this. So this is an actual lattice that is being simulated in real time using something that is a starting point of a precise physical description. That means that now these small spheres are held together with spring forces. So these are small elastic springs that are good models for the chemical bonds. I can now easily make this figure more deep, just like the figure we saw before. So there's a temperature scale here. Sorry if it's in Danish. I can reduce the dampening. And now you can see that the bonds turn red because when you have a high temperature, the bonds will be more stressed until the material ultimately go to pieces. Let me just reset here. Of course, I can also increase the lattice size and zoom in and out and so on. This is also a far more live and engaging and meaningful way of representing the figure and captions, and you can have a whole textbook hidden here in the caption here, and where the students could decide which parts they would zoom in on. Anyway, I can also give this code to the students and say, why don't you make it more physically realistic? I can give them some pointers, and then suddenly it becomes a really interesting thing where they might end up with a molecular dynamics simulation like this. This is still not like we could say pro level, but this is something that that can be developed together with the students. So when you pull one of the atoms, you can see that some red waves are being spread out. Maybe just show you how to access all the physics. Let me move this picture over here. So if I press this guy here, I get access to all the implementation parameters. So how the molecular dynamics calculation is done. This is basically solving all the Hooke's law for every pairs of atoms one by one. But I can also change the potentials to something more realistic. So this is a Morse potential, which is more representing how an actual chemical bond looks, and a lot more. Also, I can control the visuals, and I think it's maybe easier to see what I will show you now if I do like that. So if I pull this atom here and sort of, I can create like a wave that propagates through the crystal. That wave is like a vibration wave or compression wave, and it looks a lot like sound waves does, but it is actually also how sound propagates in the crystal. So with a little bit of tuning, I can get this wave to move quite far in the crystal, and I can ask the students things like, how fast does this move? The significance of that is that the speed of sound in a crystal is related to thermal transport. So that's actually a very important thing to know about, because graphene is a great thermal conductor. So asking the students to measure the speed of sound will give a first indication of whether the model is realistic. Also, you can also build in like a whole textbook here with more that description on different levels. This is just demonstrating. I didn't want to make it too long, but you can have things to try, or a multiple choice quiz where they can test that whether the knowledge that they got, or the sort of understanding they got out of playing with the model and building it at this point is working out. So then you can ask the students, okay, you can ask them progressively harder questions. How can you measure the speed of sound using the simulation? All right, I'll pull an atom and measure how far it takes for the wave to move a certain distance. Why it's so high? Then they have to think about why it is that the speed of sound, which is almost like 20,000 meters per second, why is it so high? It has to do with the light mass of the carbon atoms and the strength of the bonds. Does it agree with literature? So you can see now suddenly it's not the sandbox anymore. You have to go out and try to figure out whether this is realistic. Explain how the forces are calculated. Mention the way this model could be improved. So this could easily turn into a pretty difficult project, where at the end of the day they get questions like implement a 3D version and explain how you did it. So this is all here at this point. The atoms are only moving in X and Y. But so you need to include something like represent something like curvature energy to accurately predict how it would behave when it's sort of a real three-dimensional object. And this is something that could look like this. So here you have I would say something that built on the previous simulation, which is a molecular dynamics simulation that computes how graphene will behave if it's experiencing a shock, like a sudden mechanical push, like here in this case the substrate pushing up. This includes van der Waals forces and curvature forces and bond rotation and the usual CC, the sort of the potential energy between the carbon atoms and everything. It's still not precisely physical accurate, but that's not the point here. The point is that we show with the students, not we show to the students, but we get the students to themselves work towards making accurate physical models and validate them and explain them. So suddenly using AI does not become a substitute for teaching. It becomes something that could potentially enhance the teaching. Maybe. We're still testing this, so we don't know if this is going to work like we hope to. This is a completely different example just to show you something different, where we have a solar cell with have a nanostructured surface, and here we have three different kinds of things we're trying to optimize at the same time. First off, if we make these the gray guys here are like protrusions, like small pillars and this is a solar cell down here. And this diagram shows that if the pillars are too long and thin, they won't work because it will become unstable. That means that they will be, you can imagine all these thin needles will break off easily. So that means that out in the open, they will be worn down by objects fall on them or when they're cleaned and so on. So you can't make them too long and thin. But we can't make them too wide either, because then the droplets get trapped. So that's something that called the Casey-Baxter and Wenzel physics, which is something that where you can show that anything that has a lot of air, if you make a structure with a lot of air gaps, that allows water to not engage with the surface, and that means that they can kind of wash off more easily and fast. This is what the lotus flower is using to get its leaves cleaned, and this is what we would like to get our solar cells cleaned, that we create some surfaces with long, thin, like that with a lot of air gaps, so that the waters can roll off like a football. But now we lost the capacity of the solar capture, because we are interested in ultimately finding the balance between mechanically sturdy pillars, something that can trap sunlight efficiently, and also something that where the water can roll off and remove the dirt in the process, like in a lotus flower. So this was a way to build in make a complex physics model and have an optimization problem where the students can get the intuition before they dive into the equations. For many students, this is me included. I consider myself a student for life. For me, it helps that I have a physical intuition about the system that makes it easier to find out what is reasonable and not when I look at the equations afterwards. Of course, most of my university teaching has been kind of the other way around, but for many students, developing intuition first works really well. Once they've done that, you can ask the students to validate this model, find out how the physics are encoded behind the screen, and see and tell us how realistic is this? What would you do to make it more realistic? I'm pretty sure you can see now that there's a pattern here, that you can start off with a simple visualization and then hand it to the students and let them understand it. Of course, you don't always have time for this, you don't always want this, but it is a possibility and something that I think makes the teaching more deep and interesting. Of course, the students have access to all the physics behind under the hood, so they can play with that and try to understand what it's doing. So another example is something where I would say there are lots of things that are editors and programs that can calculate and compute and things like that for you. But what you can do is to make your own didactically focused tool that only focus on what you want to teach in a specific teaching situation. This is an editor for silicon chip fabrication, but also, to show how what we do in the clean room and how the ordering of different process steps, how that works. And because when I say how that works is that you usually know what the outcome you want from producing a silicon chip, but what you have to figure out is both the order of the process steps, which process steps, and also the parameters. And that is actually something that I created this editor in a day or so. So this simulates, this is silicon dioxide, and I can spin resistor. So this is what we do in the clean room. I can expose a pattern here. I have made it possible for us to have to create our own masks here with this editor here. So there, now I can expose the pattern, and you can see and now the area goes dark because these have been hit by the electrons. Then I guess I should develop the resist. Unlike the real world, I have an undo button, so I can go back if I make a mistake, and I can also, so you see now there are holes down in the resist. I can deposit. This is just a very simple demonstration, so those of you who are familiar with these things clearly can see that there's a lot of other things you could do. And then we deposit metal, and then we lift off the resistor, we dissolve the polymer, and this allows us to see the metal that was falling into the holes in the resist. But we can continue here and do like a wet isotropic edge, maybe not so deep, 25 nanometer, and so on. This allows us to undercut these metal pieces here. So if the students are presented with a figure like this, then they themselves can have the exercise to figure out the process steps using this software and maybe compete in making the most elegant solution. But they could also get the software because it's just HTML and they can read it with their own AI programming environment. They could work and continue on this and make it more accurate by comparing with the exact process steps that we know from the clean room. So they can take something that is a toy and turn it into something very serious. This rabbit hole goes a lot deeper. The next thing we did was to create interactive lecture notes. And I think that the next step we will take is to abolish the idea of a traditional textbook and create learning objects that are organized in a different way. But I would like to show you now what we have done and tested so far. This is an interactive note. So it's based on a PDF that we have been using for a few years in our first year physics course, where the students learn about 6 interesting themes from physics and get a kind of a first taste of some of the more complex subjects that they're going to learn later on in solid state physics and quantum mechanics and so on and so forth. So what we did was make a digital version using AI programming, which is all HTML. Advantage here is that we have much more control of how the possibilities the students have for using the text. We can pack in topics that are maybe harder or more less important, or something that is more for the curious students, into these digging deeper, so that it's easier for the students to see what is essential and what is less essential for them to read. And we can also have simulations and models built in. So this is simulating what you would measure in a graphene device like this. This showing the electronic band structure, which is important for understanding this graph down here, which is simulated measurement of what you should expect to see. Let me see if I can. Yeah, right. So let me just try to show you this kind of degree of interactivity. Means that the students can change the carrier mobility and see how the measurement curves will change. They can try to explore what it means when they're changing the gate voltage and so on. And they can go to the more advanced areas where they can see how changing the dimensions of the sample affect the measurements. So you can see that to the drawing down to the left, that the dimensions of the small illustration is updating in real time. This kind of thing is of course impossible to do with a conventional textbook, but there are literally no limits to what you can do with this. It's just basically, I feel at least, that it's my imagination that is preventing me from. Let me just show you something that I think is pretty impressive, which is that you can have a real-time calculation of the electronic band structure. So I can change the hopping energy here, or I can change the Fermi energy. You can see that the Fermi level is moving up and down like that. This calculation is really a tight binding calculation, and again, it's blurring the line between a visualization, a living graph, and the actual physics that is running behind. And then something like this code for this figure could be given to the students, and they could be asked to implement, for instance, a small finite mass, which is something that you for these electrons in the graphene layer, which is something that will result in small parabolic, instead of sharp tips here, we will have small parabolas here in a energy momentum relation. It's gets a bit technical, but another thing that is perhaps more easy to see the value of is these comments. Comments means that I can choose to open a mode where the students can comment on pretty much anything, any sort of a paragraph. They can say, I don't understand this, and so on. Can you explain it better? I could also have on the where is it? There. So this figure here can, and then they can ask questions about something about the figure, that what happens if you do this or that. But they can also make instructions to themselves on how the textbook should be improved or changed or explain something better or something like that. Let me tell you how this works. When I make a comment like that, all these comments are saved in a text file called a markdown file. And this markdown file, they can either feed to their own AI programming system and make their own version and start to adapt the textbook and build on that to create their own version of the textbook. So again, it's blurring the line between a traditional textbook and you could say a notebook that you know from Jupyter or something, some other programs where you have this sort of living notebooks. It's just far more, I would say, far more flexible here. The other thing they could do with these texts is to send them to me, which means that they get the text file is automatically saved, and they can send them to me, upload it to our learning platform, or drop it in a OneDrive folder. I will get it. That means that for the whole class of 50 students, I will be able to see which topics they are struggling with, which topics they are curious about, and which topics they would like to have explained better. So this is another thing that is very easy to do here is to, for instance, the figure I showed you before is to, for instance, in this figure here, I can. So pretty much any figure and simulation here can have a short video where I explain in a minute or two how to operate the figure or what it means or something like that. So that means that every learning object becomes a self-contained learning object, you could say, or learning item where you can have explanations and textbooks, stuff, and so on. So in the future, perhaps I don't even need the textbook in this way. Maybe I can just jump from learning object to learning object. That's sort of where the text and the equations and explanations and the simulations all sort of connected with that object. That could here the object will maybe be a graphene field effect transistor, and then the different sort of the band gap, the band structure and the measurements and the theory behind and the implementation, all that stuff is sort of bound to that object. So let me just move on. So some of the comments I got from this first version of the lecture notes here are, it makes a huge difference to the learning experience that you can actively interact with the material yourself instead of just reading a static text. Works really well with simulations. You can adjust the parameters yourself and instantly see how it affects the system. It built intuition and understanding in a fun way. A truly well-designed teaching tool and so on. I thought the interactive note was easy and pleasant to use. It made the material easier to grasp and all that stuff. Really, I didn't write these. These are verbatim some of the comments the students came with. So in this first tryout here in this fall, oh my god, there's wind. All right, I don't know. Hope you can hear me. In this fall, when we tried this out, we got we were not sure whether the students were using it or not, but apparently when I asked them a couple of weeks ago, a lot of the students were using the interactive notes much more than the PDF, and also really going in depth with these visualizations. It's still work in progress, so I don't know whether this led to better learning, but I suspect that many of the students spent more time trying to read the material and trying to figure out what goes on than they otherwise would have done. So this does not prove that it works. It doesn't prove that their learning is better, but it does prove that if you can trust a student to be aware and responsible of their own kind of learning outcome, which in my experience you can't, because they are really the ones that have most that are most motivated. That's more important for them than it is for me that they learn something. So I kind of think that that you can trust that at least these students had not just a good experience, but also felt that it helped their learning. So this kinds of learning, this kind of interactive notes are now I have made prototypes for some of the other courses I teach in the fall here 2026, and electron beam lithography is a little bit around the same kind of things here, but I believe that this sort of ideas of interactive notes can be deployed in other, not just physics courses, but any kind of teaching that involves math and models and so on, which is pretty much all of natural science and technology, all the way from biology to climate research to chemistry. I can't see where this would not be helpful. So I'm very curious to see how this unfolds. And so far, I'm just sharing this stuff with you at a pretty early stage. Yes, we worked 1.5 years, but only now we have really sort of figuring out how to consistently make these things, these learning objects. And I think we are learning as we go. One thing I'm going to try out in the fall or in the spring 2027 is to have like a collaborative mode where students collaborate on developing a physics model or optimization or something like that in real time. So that means that students who do not have great programming skills but are good otherwise good scientists, researchers, in this case physicists, can collaborate on the same object in real time, working on the code in more or less in parallel. And that means that through these AI programming tools, they can access much higher and more difficult, more complex aspects of model use. For instance, instead of just using a commercial tool where you feed in, you set your program up with boundary conditions and get the result out like a black box, in this project, you can design it so that the learning goes much deeper in how it's implemented and how the models are designed and what are the limitations, what are the assumptions made, and do a much more relevant and mature way of using models, because models in our society are used everywhere and misused a lot, unfortunately. I could mention some politicians that perhaps are throwing numbers and results around that in a different context than would be proper when they're talking about climate and other things. And I think it's very important that the people we train and we teach are like the adults in the room who really knows what a model is and when you can use it, when you can't use it, how to validate it. And especially in this time with AI splitting out information that is very hard to check, you need to have students who are strong on collaboration, independence, critical thinking, and so on. So here the students could work together on developing a model like this, but also a teacher could be part of this. That means that you can have like a co-collaboration where the teacher and the students will collaborate on developing something. I think this is pretty exciting. I mean, the whole question about how do we validate the students' level and so on is not quite as important as the students really learning to be ready for a future where things are going to change fast. So we have to make the students smart. We have to make them good at collaboration, good at critical thinking, as I said. So this sort of a collaborative mode is of course possible today with the notebooks and where people can work together on a Python script and so on. But I think that moving to HTML and moving to these kind of objects where the programming itself is not the most important thing, but the conceptual understanding of the domain, which doesn't have to be programming, but could be physics, chemistry, or biology, suddenly becomes a centerpiece. I think separating the skills in programming and the skills in conceptual understanding and modeling and so on is pretty important. So right now, we are at level 1, where the students are experiencing these interactive tools. So I hope they will say, I learned scientific methods, complex concepts, problem solving using interactive adaptive learning materials, and clearly they share responsibility for the quality of their learning. But here it's level 2. They go to from being somebody who is not just responsible for part of their own learning, but also for the teaching somehow. Because if you get the students to teach each other and teach themselves, they will get to a higher level. I collaborate with teachers and fellow students to develop my learning materials so they match my needs, interests, and requirements. Suddenly bringing students into the room where the learning is designed by giving them some of the learning, you could say, items and objects and materials to develop further, means that they will share the responsibility for the quality and the content of their teaching and learning. And at the end of the day, when they are educated and done with their, when they go out in the market and get a job, whether it's as a researcher, an engineer, or whatever, they're on their own. There are no textbooks. At least they have to find the textbooks themselves. No guidance. That means that the team lead might say, "Here's a solar cell. Figure out how to make it better. We need it to improve in this and this way." If they get a task like that, they will have to find and sort of design their own curriculum. They have to design their own course to get the knowledge that they are lacking so that they can solve the problem. I independently identify and organize the competences, subjects, and methods needed to solve a problem, and independently plan the learning of activities and materials I need. So you make the students responsible for the quality and organization of both their education and learning. And that is something I think we can bring into the university teaching and maybe even in high schools. And I think that a lot of the students that lose motivation because they're being processed like in a factory. So they're like a product. Everything is smooth. We remove all the obstacles, all the friction, all the difficulties. I think it's a big mistake. I think students want to learn and they want friction and they want to be challenged. And we are in a arms race with AI right now because AI is getting exceedingly better at answering the questions we posed to the students a few years ago. So the students can just use an AI for doing that. There's no wonder. But we have to sort of raise the bar and increase the difficulty level and the expectations and bring in more students to work at a higher level. And I mean higher level also as to get a more deep understanding. We have to fight back against the sort of the AI undermining our teaching, which is happening as we speak. And one of the ways I hope we can fight back is to collaborate with the students on it, because the students are on our side. They want to have a strong education and they want to have a job and they want to have a good career and they want to work with science and technology in their future. So they are on our side. So making them, sharing the responsibility with them, of course with guidance of experienced teachers, but practicing in handing over the steering wheel to turn them from passengers to participants to collaborators to finally pilots, I think is essential. I think it's pretty clear that AI chatbots are threatening teaching and learning. And I would like to use some homemade graphs to explain what I hope we can achieve with this work on developing engaging, interactive, adaptive, and collaborative tools using AI programming. Bloom's taxonomy is a model for a lot of different kind of teaching activities, how they are ordered in terms of their level, that you could think of remembering and understanding as sort of the base level for a student. And then when you learn to apply the knowledge and analyze it and draw connections and see the bigger picture, you're sort of, it's cognitive, is a higher cognitive level. And finally, evaluating, validating, and making decisions based on knowledge and also create new original work is something that we don't always get to. So in teaching, it is universally seen as important to access all of these levels. So you don't just teach the students to remember a lot of things, but also to go higher up in this triangle and so on. The problem here is that now we have something like this. We have a prompt that say, I would like, you can say, please create, please evaluate, please validate. And I think that's a big challenge. I know I say undermining, that's what I mean is really that the way that we usually teach is challenged heavily by the fact that the students now have a helper that can do it all for them. So we have to create more complex, more sophisticated, and more challenging and harder problems for the students to not lose interest and not lose the opportunity to have a strong education. So yeah, you could maybe say it like this. If you think about like volatile learning is when you're having students just watching movies. Basically, they're watching somebody else solving the problems. They would lose skills. They don't feel ownership. That means they don't feel that they did it. They will be their cognitive abilities can only decline. They don't feel responsibility. So if they make something that don't work, well, I didn't do it. And they feel active, but they really aren't, because they're just and it's a passive form of activity where they feel they're working, but they're really just working on getting somebody else to do their work. So what I hope we can do with this is to create pilots where they will master their own competences and master their own learning, and they will feel higher ownership of what they're doing because they feel they're in control. They're in the pilot seat. They are making the calls. They're not just asking the AI, what is it that I should be doing now? But they're orchestrating AI agents maybe in solving problems for them. They would have higher responsibility, and perhaps we can even make them smarter. And I think making smart students smarter is one of the most important things right now, and making them truly active. So that requires us to increase the activity level and the friction, which means that the difficulty level and sort of this, well, I could say struggle, or that you have to fight the material. You have to be something that challenges you, just as you, when you maybe go to a fitness studio and something and lift heavy weights, you accept a certain amount of stress and discomfort maybe even, or struggle, because you know that this will make you stronger. And I think students are smart enough to understand that they don't learn anything from being passive passengers. They have to be in control. Our duty is to figure out a way to organize their studies so that they have this possibility. So maybe we have a situation like this where instead of the little bit depressing version of this triangle I showed you before, that they can access this basic level by visualizations that build retention and memory, and make them understand and remember things, and also integrating the conceptual knowledge and giving them intuition. This apply and understand is pretty much meaning that they will understand how models work and how to apply them to problems. Validate and analyze the relevant scope and limitations of the model has never been more important than it is now, where complex calculations and predictions can be generated 100 times faster than we can. We are the adults in the room. We are the humans in the loop, and we have to teach the students how to validate and analyze when a model is appropriate, when the results can be trusted, and what are the limitations, and also how to improve them. And finally, building your own model, improve it and validate it is something that our students have been doing all the time, but not all of the students. And I think that more students can learn in a responsible and proper way to be in this creative process where they are also developing models on their own. At least that's something I kind of believe, and you know, we need evidence, so we are studying this and trying to measure how the students respond to this kind of learning. So after 1.5 years, we are still learning, and it will take a while before we are really sure of what we're doing. But I would like to share with you my thoughts so far. This is all work in progress, so we don't have any, we don't know so much yet, but I firmly believe that those who work learn. I think it's backed up by literature. Watching somebody working is not enough. A baby doesn't learn to walk unless they try themselves, and you cannot learn to play the violin unless you play yourself for hours and hours and hours. So we need to create a working a learning strategy that makes the student work. So AI chat and AI coding make difficult tasks easy and slow tasks fast. Sounds great, but it actually makes point one difficult, because suddenly the students don't have to work in order to produce the results, to answer our questions. So we have to find different questions, and maybe just not questions, but like engage in a kind of a more deeper collaboration with the students on giving them strong competences, because AI is challenging the education, and we must find a path towards sustainable learning, meaning that the students' competences and knowledge is not being outdated in a few years. So I think the most important thing is to give students a deep foundational competence, and also teach them how to be adaptive and smart. So if they are able to think well, I think the brain is definitely and will always be the student's most important tool, much more important than AI programming environments, because that's sort of the way that they will be able to raise their academic level, and they can have critical thinking and independence, and still building on their strong foundational competences. The brain is what is important. So, but I think these tools can strengthen the adaptive and dynamic and effective learning, as we just saw. But I also think it has to be done right. And what is right? I mean, we don't know yet, but we are collecting evidence based on our experiments with, deploying this stuff in courses. And I think that before we make any real changes and make any real conclusions about the effectiveness of this, we will need more evidence. So we are still trying these things out and developing as we speak. I hope you found it interesting. I'd like to thank my collaborators at DTU Physics in the Digital Experiments Group, Bjarke Sørensen Jessen and Søren Raza, and also thank the DTU's AI group. If you have comments or questions or feedback, feel free to put them in the comment below, and you can also contact me if you have any questions. This is all work in progress. We are don't have a product to sell or give away right now, but I hope you found it inspiring. But I think my main message is we don't know yet to which degree what I showed you is effective and desirable and meaningful. We think so, but it's work in progress. So if you copy this or do something yourself, just want to encourage you to be cautious and curious, and don't believe the hype, but find out for yourself whether a particular kind of AI enhanced teaching or learning actually improves the outcome of the students, not just the reports they make, but what they actually learn and are able to do. Because we really need to focus on the students, not the reports and the stuff they produce, because it could have been used with AI, but we need to know what goes in that the students develop. So with that, I don't have any more to say, and thank you for attention. And with that, I think I need to enjoy some time in my lovely garden this beautiful Saturday. Cheers.